Welcome to the last lecture of probability and random variables in unit 1. Here we'll deal with continuous distributions. So in the last lecture we have seen discrete distributions, Bernoulli, binomial and Poisson's, whereas in continuous distribution we are going to see here uniform as well as Gaussian distribution. Whereas there are other distributions like gamma distribution, Rayleigh distribution, Rayleigh distribution. So there are many such things, but we are seeing the most important continuous distributions here. Let us start with uniform distribution. So where do we use uniform distribution is whenever we see an application where in between a particular range the value is uniform, it doesn't vary, it's a constant, then we go for uniform. So a random variable x is often used where we have no prior knowledge of actual density function and all continuous values in some range seem equally likely. So this is one important term which we have to remember. Equally likely means if all events are equally likely, it means that they have same probability, equal probability. So if all the values in the range, in a particular range, are having a constant, that means equal probability, and I don't know the value, I don't have prior knowledge about a signal. For example, I can take an example of a signal processing. If suppose I don't have prior knowledge of a particular signal and I want to estimate its probability, then I'll assume that that signal is uniform over a particular range. So this is a very important distribution which we now practically use it in signal processing. So coming to its distribution function, a random variable x is called a uniform random variable over an interval a comma b if its density function is given by, so fx of x, it is continuous, so it is fx of x is equal to 1 by b minus a in between a to b. You have to observe here a less than x less than b, so there is no less than or equal to symbol. That means at x is equal to a and at x is equal to b, it's not equal to value. It is only a constant 1 by b minus a in between a to b, otherwise it is 0. So it looks like a step function. So let me show the function here. It is in between a to b, it is a value constant, it is 1 by b minus a. It is not equal to a and also it is not equal to b, but it is in between a to b. So coming to its distribution function, how will we write its distribution function? The relation between distribution and density is like this. If I want fx of x, what I am supposed to do is I have to do the integration of it. So fx of x is equal, when x is less than or equal to a, so if seeing this itself we can estimate its distribution. Less than a, it is 0, and in between a to b, what is its value? It is 1 by b minus a. Integrate it, integrate 1 by b minus a dx, which is nothing but definitely equal to, but in between a to b, so it is x minus a by b minus a in between a to b, and maximum value x greater than or equal to b, definitely it will be equal to 1 because you add both. So how it actually looks like? So at x is equal to a, it is x minus a. If you see the distribution function, x minus a by b minus a, when x is equal to a, it becomes 0. So that's why at x is equal to a, it is 0. Similarly, what is the value at x is equal to b? X minus a means b minus a by b minus a, which gives you the value of 1. So the maximum value is 1. So this is nothing but its distribution function. So the uniform density function and its distribution function over a period a to b. So coming to the Gaussian distribution, the most important distribution that is actually currently practically used to estimate anything. If you take any general example like the population in Hyderabad city is Gaussian, and the population, for example, in the population, the amount of girls that are present, or the number of boys that are present, or the number of patients in a particular area, always it approximates to be Gaussian distribution. Okay, so how will it actually look like? It is an exponential function. A random variable x is called a normal or a Gaussian random variable if its density function is given by fx of x is equal to 1 by square root of 2 pi sigma. Sigma means nothing but standard deviation, variance, e power minus of x minus mu whole square by 2 sigma square. Mu was here mean. So you can see how it looks like. So this is the Gaussian density function having its maximum value at mean mu, which which is 1 by square root of 2 pi sigma. So at mean mu, it will have the maximum value which is equal to 1 by root 2 pi sigma. And how will it look like? At mean is equal to 6. You can see that you will have maximum value like this. There are three functions here. What is it actually varying here? The spread in the density function is actually varying here. That spread is nothing but the variance. So you can see a variance is equal to 0.5, which is less spread. Variance is equal to 1, a wider spread. Sigma is equal to variance is equal to a more wider spread. So at mean is equal to 6, it is a peak value. So that is Gaussian. And coming to its corresponding density distribution function, definitely it is integration 1 by root 2 pi sigma minus infinity to x. Don't forget that, minus infinity to x e power the same function. When you want to solve this mathematically, it is not so easy because in the form of e power minus x square by 2 d sigma. This is actually approximated using an important function called as error function, which is phi actually denotes the error function. So error complementary function. So error complementary function, it is nothing but a, in the appendix of the textbook you can find a Gaussian table, which is nothing but a normal distribution chart. Like a log chart, you'll have a phi value. So those phi values, whenever you vary x minus mu, how many deviations it is away from the mean, divided by sigma, the variance, how much it is varying. So that gives you the Gaussian distribution values. So this is a very, very important concept. So we have to remember both uniform and Gaussian distribution functions, its density functions as well as its distribution functions. And if you see how it looks like, the distribution function is maximum. Always see, you can see any distribution function, it is monotonically increasing function, but maximum, not maximum value, the middle at mean mu, it is exactly 0.5, middle value. So where do we use Gaussian? Study of random phenomena. So whenever I want to study any random phenomena, for example, the current, or if you want to estimate a parameter which is random in nature, then I'll use Gaussian. And you will use when you have more number of random variables. If suppose I want to sum all independent random variables, I want to estimate the sum of all the independent random variables from 1 to infinity, then we'll use it in central limit theorem. So you will have an important fact, will derive an important fact there, that the sum of random variables, if each random variable is Gaussian, the sum also approximates to be Gaussian. This is a very, very important characteristic of Gaussian, which is actually called as central limit theorem. So also this is also called as normal random variable, and it is represented as, always it is represented as n of mu comma sigma square. Thank you. We'll stop here.